different transformers. Some of you came from transformer manufacturer factory. Some of you came from educational institutions. Some of you just doing some modeling work with transformer as a fun. What is the transformer for us as power engineers? It's, in one hand, a transformer can be considered as a very simple device. It has only one task: to transfer energy from power plant to users. On the other hand, a transformer is a quite complex electromechanical, electromagnetic, or even a thermal device, because it has a lot of subparts. Now we are just dealing with the transformer in electrical engineering point of view. Just a fun. Can you see my screen now?
Yes, we can see it.
Yeah, okay, because that green frame has disappeared. As you see, we have been taught at the universities or even at technical schools how a transformer model looks like. It's a very simple one. It consists of 3 inductances and 3 resistances. What's the problem? Why do we need any sophisticated software to simulate, to model the transformer? Because if we go in more detail, more deeply into this single phase circuit, each component can have some complexity. Even the winding resistances could be frequency dependent, or the magnetizing inductance can be nonlinear, or the iron core or the resistance representing the iron core losses could be, or it is, a nonlinear object. So let's talk about some words about what is nonlinear and what is not in a transformer model. Of course, the magnetizing core is nonlinear. We can handle nonlinearities in different way. We can consider the nonlinear magnetism or the flux current relationship as a single value or 2-valued relationship. We can omit hysteresis. We can do so with some consequences. One of the most significant consequences that if you use a single-valued non-hysteretic characteristic, you cannot simulate the residual flux. What is the meaning of, or what is the importance of the residual flux? In the next slide, you will see that. What is the relationship in between voltage, the applied voltage, the excitation voltage, and the flux and the no load current? You can see this diagram. It's a very basic one. The voltage, the integral of the voltage equals to the flux. If the flux reaches a certain saturating value, the current is getting to be non-sinusoidal. It's clearly visible on this picture. If the flux reaches this region, on that hysteretic curve, reach a point where the current and flux has some more complex relationship than to be a linear one. Further, if we have a residual flux, this integral, the voltage integral, which is the flux, can be shifted up and down like as a DC flux, or like as a DC shift on this flux scale. And the dotted line shows the flux versus time without hysteresis, without residual flux, sorry. If we take the dotted line, the inrush current, the amplitude of the inrush current can be quite moderate. But if we consider the residual flux, the peak of the inrush current could be even higher. It's depending on the polarity and the amplitude of that residual flux. So that's why considering remanent magnetism or residual flux, it is important. What are the consequences if we have a nonlinear transformer, or if we consider the nonlinearities? If we experience a high inrush current, on the other hand, it will have some mechanical and electrical stresses on the windings or the fixing of the windings. If we have a nonlinear transformer, it can resonate. Mostly it can resonate with the capacitances of the grid. If we have a nonlinear transformer and the relationship in between the voltage and current is getting nonlinear, it might have some consequences to the operation of our protection relay system. We know very well that in case of a transformer differential protection, the biggest problem is how to solve the issues caused by inrush current of the transformer. The similar issue may appear even for overcurrent relays. Sorry, I see some typo here, I will correct it. If you energize a PV park or a wind farm, many similar transformers are energized simultaneously. So the inrush current amplitude is rather high. If the CT's current transformers saturate due to the high inrush current amplitudes, the secondary current of the CTs will not be proportional with the primary. We feed the relay protection from the secondary. So if the CT saturates, the protection device will receive something different than a signal that would be proportional with the primary current, and so on. It's an issue when we energize a bigger power plant or a bigger wind farm, that when you energize these farms, these transformers, the current is very high, and this high current will result in quite high voltage drop or voltage dips at the connection point. The sympathetic inrush current phenomena is another one. So if you would like to develop a transform model to be able to simulate all of these issues, we have to specify the frequency range of interest. As I written in the invitation of this webinar, now we are developing a transform model for low or mid frequency range. According to SIGRI Study Committee 33, this region is this one, transform energization studies. This frequency range is typical for transform energization studies or resonance studies. So we don't want to create a model for higher frequency than 1 kilohertz or around. Okay, what input we need to design a reliable transformer model? Sometimes we have to know some internal secrets of the transformer. Sometimes it is difficult to get. What is the core structure? Whether this transformer is constructed as 3 single-phase device, and we use it as a 3-phase unit, but built individually, or the transformer is a real 3-phase device, 1 3-phase core in a tank. And unfortunately, the core design is very rarely shared by the users. Sometimes we need this information as well. Sometimes it's not so important. If we have at least 1 delta winding, it doesn't matter what is the actual core structure, either stacked one 3-leg stack core or 5-leg or 4 or 5-leg stack core. Let's move on to the modeling side, to the user interface side. Nowadays, we use ATP Draw as an interface for AMTP simulations, and we have several modeling options to work with transformers. As you see here, these models are grouped on the floating component selection menu under transformers, and we have right now 6 different options. Now we will concentrate more on to BC-tran or hybrid transformer model and some words about the saturatable transformer model. I myself don't like the ideal single or 3-phase model because it's more mathematical than physical. So if you work with, sometimes it works perfectly, sometimes it produces some strange behavior. Let's go a bit more deeply into that transformer modeling option. If you know how many phases you have or how many windings you have, how many windings per phase you have, sometimes this information is important because you can decide the appropriate model according to this information. For example, if you have four windings per phase, you have no option. Only option which supports more than 3 windings per phase is the hybrid model. If you have 2 or 3 winding transformers, you can work with saturable transformer model or BC-tran. Okay, so today we focusing on that blue transformer models. How the saturable transformer model looks like. Very easy, very similar to the equivalent diagram I showed to you at the first slide. Only difference that now the nonlinear magnetizing inductance is there. Even HTC model support different combinations of windings, different winding structure. Here you see that HTC supports either Y, delta, zigzag, or auto connections. BC-tran doesn't support zigzag connection, but YD and auto transformers are supported. Hybrid supports all combinations. So this is also an important information sometimes, because not all models supports all winding structure. The advantage of HTC is its simplicity. The disadvantage is that you have to calculate these resistances, inductances by hand. If you are familiar with transformer manufacturer catalog or transformer manufacturer design data, you can calculate them easily, and thereafter you can use ohms inductances directly. BC-tran model is a more sophisticated. Basically, or originally, the BC-tran model has been or still is a linear relationship in between the primary and the secondary voltages and currents. So the original BC-tran is a linear transformer model. If you would like to simulate nonlinear phenomena, you have to complete this linear model with objects capable to consider the nonlinearities. The advantage of BC-Tran is the very straightforward input information. You can use the transformer's nameplate data directly. You need just the MVA rating, the nominal line-to-line voltages at both terminals. You have to know the winding connection, Y or delta. You have to know the short circuit impedances, short circuit losses, and no load currents and losses, or some information about the no load test or excitation test of the transformer. Generally, these data are readily available for each transformers. Unfortunately, sometimes it's not so simple to separate different type of losses, because we know very well that the no load loss is the sum of the eddy current loss and the hysteresis loss of the iron core and the transformer. So if you have any idea, you can share them equally, or you can put a bit higher weight to the hysteresis, so share them 1/4 and 3/4, for example. How to connect the nonlinear external hysteretic or non-hysteretic inductance to the BC-Tran? The general advice is to connect these nonlinear elements to the winding which is closest to the iron core. Normally, this voltage is the lowest, is the winding with the lowest nominal voltage. So if you have a Y delta connected transformer, 100 kV, 10 kV, 10 kV winding is always closest to the core. So you can connect these nonlinear objects to the secondary, to the lower voltage winding. Hybrid model is a more sophisticated, even more sophisticated way of transformer modeling than the BC-Tran itself. We can work with the same test reports as we used for the BC-Tran, but there are two additional options. We can use design parameters of the transformer. I will show to you what design parameters mean. Very few of us has access to these design parameters, but we can work with typical values. Sometimes we are not informed about the capacitance of a wind farm transformer, because this information is not there in the transformer manufacturer datasheet or manufacturer test report. So it's very useful to use typical values in that case, because sometimes very dangerous if you omit the capacitances, especially if you have a delta connected winding without any connection to the ground reference. The model can produce quite unusual behavior. So the best option to connect each windings to the ground with some impedance, and this some impedance can mean a stray capacitance of a delta connected winding to the tank or to the ground. If you don't know it, it's not a problem. You can choose typical values, and you will have a capacitance there. Internally, the hybrid transformer looks very similar to the BC-Tran. Actually, the BC-Tran is there inside this model, but some additions are also there. For example, the frequency dependency of the winding resistance can be considered. And the capacitance in between the phases, in between primary and secondary, in between windings to the tank and to the core can be considered by a capacitance matrix connected to the primary and the secondary. Of course, if I show to you the internal structure of the hybrid transformer model, we can conclude that it's quite complex. Very often, or most of the cases, the user don't need to deal with this complexity, because if you use correct data, reliable data, all these couplings, all these sub-inductances or capacitances shown in red are calculated by the software. So we will work with these models. Let's talk 2 slides. Don't be surprised. Sorry, this number is wrong. I will have just 20 slides, no more. So these slides show something about the design information or the design data. If you work with the hybrid model, you need to have these data in hand. What is the difference in between the low and the high voltage winding? What is the difference in between the core and the low voltage winding? What is the difference in between the core, the outer layer of the windings, to the core and to the tank, and so on? If you have this data, you can construct a transformer with hybrid model. If you have just transformer design report or factory test report, you can exclude, or you can take this data from this report. As a conclusion, this is the last slide before we go into the practical part, which is important and which is not. This table is also coming from the SIGRE 33 working group. Saturation is very important for low frequency studies. Iron core losses is also important. Eddy current is also important. So if we are dealing with these low frequency range studies, the first 4 factors, the short circuit impedance, the no load losses, the no load current, eddy current losses are important. The capacitances between the windings to the tank or interwinding capacitances are not so important. This table tells we can omit them. It doesn't mean that you can omit them completely. I never suggest to replace these capacitances with 0 capacitance. If you have no idea, use a 1 nanofarad, 2 nanofarad, or in that range. Okay. So that's all about the theoretical background, and let's go a bit into the practical side. The practice means I will use ATP Draw and prepare 3 short documents to share with you. First, we will develop together a wind farm model, wind farm transformer generator, step-up transformer generator model in a wind farm. Can you see this document now?
Yes, we can see it.
Okay,
Laszlo.
Thank you, thank you.
Just enlarge it.
Yes, I will enlarge it this way and that way too. What we have? The transformer is a 2.8 MVA unit. Typical voltage is 33 to 660 volt at the secondary. It's a typical VTG transformer. We have typical data. What does it mean? We know the frequency, the nominal voltages, we know the coupling, the connection of the windings at the primary and the secondary. Even we know the phase shift. It's DY11. Normally, we have an open circuit test report for transformers in that range. Open circuit test, unfortunately, is made only at the nominal voltage. So we have only one information. What is the no load current at 100% nominal voltage? Additionally, we have an information about the open circuit loss. Of course, we have short circuit impedances.
Laszlo, sorry to interrupt you. Perhaps can you take out the paragraph sign? That's
Yes.
right. That's much more better. Thank you.
Sorry. Yeah. So we have two losses, one open circuit loss and one short circuit loss. Of course, taking the nominal power, nominal voltages, we can calculate the nominal currents at either side of the transformer, or if you like, you can calculate the nominal flux of the winding. Because some parameters are related in percent, it's nice to have these nominal data in ampere or in volt seconds. We can convert these data from each other easily. The task of this short practice is to fit this transformer model to the inrush decay phenomena provided by the transformer manufacturer. At the design stage, you have no option to take any measurement on the transformer, but generally we know how the inrush peak decays versus time. This information is important for all voltage dip studies. So I had a try to fit this transformer model using this data to the curve provided by the manufacturer. As you see or don't see, the numbers might be very small. The currents are given either as RMS, this is the dotted line, how the RMS current decays within from 0 to 1.5 seconds. Or the same diagram is shown as a solid line. This one is given the same information, but the peak current is displayed now. So we need some parameter fitting to be able to reproduce the behavior of the transformer and to reproduce this behavior, you can use just a single phase model. As you see, it's much more simple. We need just one nonlinear inductance, a single phase transformer, some stray capacitances, and an ideal voltage source, and a flux meter to record the flux versus time. I can open ATP Draw and I will also try to enlarge a bit. You still don't see, but I will share it soon. Okay. So this model is here. The BSPTran input dialog box is very simple. You enter single phase MVA power, phase to ground, RMS voltage at the primary and the secondary, and you enter just the nominal voltage excitation current. That's all. What is important is to use this external LM option, because the most straightforward one if you use the linear internal modeling, but if you choose this option, the transformer will not operate as we intended. So this option is very useful, and at the same time, don't use auto add nonlinearities, because if you choose these two, the program will use this information and will connect the nonlinear magnetic core to the model internally, so you cannot use this hysteretic inductance. Because if you choose this auto add nonlinearities, even if you specified the nonlinear volt current characteristic, the program will just use a so-called type 98 and type 99 nonlinear inductances and nonlinear resistances in a non-hysteretic way. So if you would like to represent the hysteretic loop, you have to switch off the auto add nonlinearities and use an external inductance. If you do so, you can represent the hysteretic loop very easily, or even you can represent the no load current. I always suggest to apply some basic tests, whether this model is appropriate, works as you expected or not. What does it mean? What you expect is to reproduce the no load current and to reproduce the short circuit impedance. The parameter fitting at the beginning was not a success. If you consider the total short circuit loss provided by the manufacturer, the damping is much faster after inrush current peaks. This damping is important because this damping is the main factor. It's a main controlling factor for the voltage dip. So this fitting showed that not the total short circuit loss has to be considered, just the 73 or 70% of it. Why? Because transformer manufacturers always considered that the temperature of the winding is at the nominal 65 degrees Celsius or 90 Celsius, depending on if you have an oil field or a dry type transformer. So at the design stage, or if you take this measurement on a cold transformer, the losses are significantly less than the nominal losses. So this way you can correct or override the manufacturer provided short circuit loss. Actually, it is not 15 kilowatt, it is just 11 kilowatt. If you enter these data into the BC-Tran dialog, the damping will be exactly as the curve we have seen at the beginning. Okay, if the single-phase model works, now we can create a three-phase model. How a three-phase model looks like? It is very similar. You need three-phase source, of course. You need a three-phase transformer. In such a case, you can use the grouping feature of ATP draw very effectively. As you see, this object cannot be found in the component selection dialog. Even if you look through all of them in the list, you cannot see such an object. Yes, because it's a group object. If you select it and go into this group, you can see the standard BC-Tran object. So this is a three-phase transformer model. We can use the manufacturer data directly. We can connect the nonlinear inductances to the secondary. As you see, sometimes it happens that the program lost the winding connection. Never mind, if you go into and define the winding connection again, it was a delta connected at the primary and Y connected at the secondary, and I think it was 33 phase shift. If you go further, the parameters are calculated and you can click OK and you get the model. A trick maybe for beginners, I don't know exactly who is new to ATP draw and who is not. When you click on OK or run ATP, there is something happens in the background. As you see here, the ATP simulation is activated and the new electrical parameter of the transformer is calculated in a DOS window. If you don't see this DOS window, you will not see if any error occurs there. So I very highly recommend to run ATP draw this way, otherwise you have no chance to see what's wrong. At the end of the session, if you have questions, I will show to you how to activate this DOS window to be visible. So it is there in the background for me. Okay. Now we have a new window, new model, so we can go back to the original circuit. What we expect from a three-phase model? At least we expect that this transformer would behave similarly than a real transformer in case of short circuits and in case of no load excitations. So let's do a test on a different transformer. How to repeat the factory test of the manufacturers? It's very easy. If your model fails on this test, it surely will not work in a more complex or more sophisticated simulations. Let's move this part out. If you apply a short circuit here and disconnect these voltage sources, now you have an excitation test at 100% voltage. And the transformer operates in no load condition. So we expect a current to be equal to the nominal no load current. In that case, it is less than 1 amps measured at the high voltage side. Here you see the nominal data of the transformer. If the current is around 0.15%, the current is there. How to check it? Easily. First, you can disconnect any nonlinear objects. Because this measurement is made at nominal voltage, you may expect that the transformer core could be linear or doesn't saturate significantly. So you must be able to reproduce this test by using a linear transformer model. So now you can switch the linear option on. And make a test at 100% excitation. As you see here, the current is exactly equals to what we expected. Another issue, how to measure the currents, how to display the current measurements online. It's quite new. During the last session of this webinar series, Professor Hoydalan showed it to you. There is a steady state enable checkbox. So you can display the currents, the absolute value of the currents. Some scaling is needed to get it in RMS value, but it is very important not to use 0 here, because if you use 0, this steady state screen display will show to you only the steady state initial conditions value calculated by ATP. And as you know, if you have nonlinear elements, the steady state initialization is not 100% perfect. Only the linear part of nonlinear inductances are considered in the steady state at 0 times 0 initialization. So the trick is to use a higher number here, because this meter will use an FFT radix algorithm and will calculate the current phasors at this time window. It's just a trick. If you don't like that, you have two additional options. You can measure the RMS values using these objects. This object is there in the power system toolbox. It's also useful because it gives a true RMS. So whatever you are using, you must be able to reproduce this current. And of course, if you have data at higher voltages, higher excitation voltage, you can increase the excitation voltage. For example, it's also not very known, or maybe not for everyone, that if you connect different sources at the same node, it's on the screen, it looks like as they were to be connected in parallel, but actually they are connected in series. So now I apply 120% excitation voltage, and you can check what is the steady state no load current at that excitation. If you have manufacturer data, you can check it easily. Similarly, if you switch off this source and switch on this source. What is that? This source, the amplitude is 15%. 15% is the short circuit impedance. So now you excite this transformer with a 15% voltage. If you apply a short circuit at the secondary, now we are reproducing the short circuit test. What is the current we expect here? It is exactly the nominal current of the transformer. Nominal current at the high voltage side using this nameplate data is more than 500 amps. So if you run this simulation, you will get the short circuit current here, the nominal short circuit current here. If the transformer model works this way, satisfies the steady state short circuit and open circuit tests, you can move further. Now you can switch on the nonlinear inductances. You can switch to external nonlinear modeling. And now, if you wish, you can reproduce this test. First, the no-load test. And you see that even using the nonlinear inductances, we get a very, very similar value here. It's not exactly the same, of course. It is because this number is coming from an FFT analysis. If you take a look to this value, we need a plotting program to display the true RMS value in all phases. You can see that this value is exactly agrees with the requested or expected value. So this display and the true RMS value are not exactly the same, very close to them, very close to each other, but not exactly the same. So test, build the model step by step. Otherwise, there is no chance to get reliable transformer model. Let's go run quickly on this document. If you have a reliable transformer model like this, you can reproduce the no-load test. You can display the nonlinear hysteretic behavior of the core in each phase. As you see here, even the residual flux, the pre-specified residual flux can be seen easily. Here it is positive, here it is negative, and in middle phase it equals to 0. And thereafter you can use this transformer, for example, for inrush studies. And of course, you can change many parameters. I will share these documents with you, with Professor Grigoris, and he will share it with you, or I can upload it to the EEUG site. Finally, one more examples. I would like to share one more examples with you. This is a typical study I prepared some years before. It's a voltage dip study. The system is a bit more complex. It was actually a Japanese system, 60 Hertz system, 275 kV, double circuit transmission line supplied the power plant. And if you energize the general step-up transformer here, the system is weak, so the voltages dip significantly at the PCC, at the point of common coupling point. The transformer data are known. You can use this data to develop a nonlinear transformer model. And if the model is fully tested, you can do different studies. And I will show you just one result. The inrush current is high. The voltage dip or the voltage distortion at PCC is quite significant. If you calculate the RMS value of the voltages at PCC, you can see that the voltage drops significantly, far below the acceptable 98%. And this voltage dip occurs only in two phases where the current is high. In red and the blue phases, the current is high, so you get a high dip on voltages. And finally, very finally, I will show to you a transformer modeling, a transformer model of an XFMR hybrid model. Some years before, I gave a course in a factory in South Korea. And of course, it was a transformer manufacturer, so they had design data. Design data means information about the core, about the arrangement of the windings. So if you have this data, you can use the modeling option, so-called design parameters. If you don't have these data, you can use just the test report. And this way, you can see a very, very similar windows like for the BC-Tran. If you wish, even you can omit the capacitances completely. It is also not known that if you right-click, you can switch off completely the capacitance option. So in that case, the hybrid model will work without capacitances. If you don't have, you can choose typical values and you will have some capacitances there. Okay, I think we have no more time left. As a conclusion, I can say that working with nonlinear modeling is not the most simplest modeling with ATP. It's much more complex than working with transformers in any load flow software or in any voltage control studies, because in these studies, the transformer is a linear device. But if you use the suggested step-by-step model development stages, there is a chance that you can create your model within some hours effort, not within minutes, within hours. If you already have one working model, there is a very simple trick. You can scale this transformer model, the working one, easily, because if you know the hysteretic curve, it is tested, it works as you expected, you can keep this curve forever, because you can rate this one to a transformer with different power rate, with different voltage level. If the voltage is higher, you can simply multiply with the new voltage level. If the power is higher, you can simply multiply on this curve on the current scale. Even if the frequency changes from 50 to 60, you can adjust this curve. So don't drop the already working model and start from scratch. You can use what you have, because you can use Excel effectively. If you have a model here like this, you can, this is current flux. You can simply Control C and go back to this screen and use paste. And you already have a new nonlinear characteristic. You can check it with you. As you see, it has completely changed. Okay. That's all from my side. The time has run very quickly. I created several project files for this webinar. I created 6 files here, each of them working perfectly. I can share it with you. We will discuss with EEUG team members. It could be either possible to upload it to the ATP Draw site. You know that atpdraw.net, there is a file sharing area, so I can upload them. So you can play a bit, you can make some tests, and hopefully they will work also for you. If not, you can have a question like now.
Thank you very much, Laszlo. Excellent presentation. Of course, there were some questions about how they will have access to the documents and the data, but I'm sure that you answered them properly. There are some open questions already now. First of all, there was a question that was set in the very beginning. It seems that there is no single-phase version for the hybrid model. Could you please explain the reason?
Because Professor Hoidalan has not implemented it. I don't know theoretical reason. Because there is BC-tran behind, and BC-tran supports single-phase transformers. So I can imagine that it's just a program development issue. But what you can do is to take a 3-phase transformer and select the triplex option, because this way a hybrid model will work with 3 individual single-phase transformer. There will be no any connections in between the phases, either magnetically or through capacitances. So this option may help if you really have a single-phase transformer.
Okay, we have a question also that has been already partially answered by Delcho. It says that test transformers age. How should the modeling change to account for the aging, or should it change at all? For dry type as well as oil field, I have tested a lot of transformers. The power factor tests of the insulation are a major criteria to approve continued usage of transformer. Wondering what parameters change as transformers age and how that affects the response of the transformer to transients.
The insulation is aging and it will change the capacitances a bit, but capacitances are just a secondary importance in these type of studies we were talking about today. What else is aging? Oil is aging, it's not an issue. I don't think so that the copper loss or the resistances, maybe the resistance, because the winding resistance also includes the resistance of the connections, but I don't think so that in a part for a power transformer the resistance would be different if the transformer is aging. So I don't think so. It's an issue.
Okay. Another one is for auto transformer modeling to model nonlinearities. Is XFRM the most suitable model?
You can also use BC-tran. The only limitation I know related to XFMR, the hybrid model, that you cannot work with the residual flux. XFMR supports, if you go to the core modeling and go to settings, you can choose which type of nonlinearity will be used. You can have an option to change to hysteresis. Even you can change the number of points on this lower part of the saturation curve, but it cannot be higher than 8. In some way, it's a limitation. If we go back to the saturation model I used, as you see, I use at least twice of it. So the characteristic must be smooth enough to get stable operation. I don't think so that 8 is enough. The other option that other limitation that you cannot set residual flux in any way. Why in case of BC-tran modeling, you have full access to the externally connected type 93 nonlinear inductance, and you can set the nonlinear, you can set the residual flux as I showed to you. I think it is set here. Yeah. No such option exists with hybrid model, or at least I don't know how to set it. Of course, a trick always works, a very simple trick always works. You can see this trick on example 9. You might familiar, or some of you might familiar with that example test file of ATP draw. It is there in the example collection. Here you see a non-standard switch. It's also a group. It steadily energizes the transformer. Thereafter, it disconnects from the source and reconnects. When you disconnect from the source, even if you use hybrid model there and the nonlinear core is represented as a hysteretic model, the residual flux could be represented this way, because the residual flux is not an input data, but it is set by the system when you de-energize the transformer from the grid. If that was the question, how to represent. The question about auto transformer. Yes, I suggest to read carefully the auto transfer modeling in ATP draw manual. There are some pages about that, because the program internally recalculate the short circuit impedances required by the auto transformer modeling. So the user don't need to do that recalculation by himself or herself in advance. You can use directly the manufacturer data, and this recalculation is made by ATP draw internally. And I think it is also made on hybrid transformer modeling, because the BC-tran matrix, inductance matrix, is the same.
Okay, we have also some other questions. How can I model the R-core reactance if I have no information from the manufacturer? Good question.
I can reply in a simple way. If you know the short circuit impedance of the transformer, seen from the secondary, seen from the lower voltage side. Just use this impedance and multiply it by 3, 2 or 3. You will have the air core inductance. And you can enter this air core inductance here. Because the last slope, the last section, last current and flux points define the air core inductance.
Okay.
The air core inductance, I will try to show. The air core inductance is here. This is the saturating point, and thereafter you will have a straight line, much like this line. The steepness of this straight line is defined by the last and the first before the last point on the flux scale and on the current scale. So you can simply calculate it using this Excel, using d phi divided by di ratio, and you get the air core inductance. So in case of BC-TRAN modeling, it is there in the hysteretic characteristic. In case of hybrid model, it is there on the setting page here. So you can enter it directly if you know this number. It is a very, very small number in millihenries, sometimes just 0.001 millihenry. If you have no idea, you can choose this estimate. The program will make a try to estimate it. So that's all I know about it. This final slope on the nonlinear characteristic is very, very important in inrush studies. So you must pay attention.
Okay, another question is, are sweep frequency response analysis tests also useful in implementing the model?
I had a slide on my presentation. It was entitled Does and Don'ts. And the first item was there that we are talking about the time domain modeling. So no FRA, no finite element modeling is included in this webinar. The answer is simple, because I don't know, or I don't know these modeling tools. So ATP draw, as far as I know, ATP draw right now supports only time domain or frequency domain modeling in some way, but not FRA analysis input data can be used for transformer modeling. Maybe colleagues in the EEUG side knows more about it, because I some years or some months before I read some words about that some work is underway about this model development, but I personally don't know anything about that.
Okay, another question is it possible to set a percentage of remnant flux using XFME model?
Percentage of remnant flux in XFMR. In XFMR, you cannot set the remnant flux in any way.
Okay. Is there a minimum slope for core currents in XFMR open circuit test? It seems as if sometimes small differences between currents lead to no convergence of the XFMR model. For example, 90% voltage, 0.042%, 100%, 0.046%, and etc.
It's too complex question. As I said, if you are able to calculate the last section, the slope of last section, you can enter this data directly here, either in per unit or in millihenry. If you work with XFMR, if you work with type 93 hysteretic inductor, the slope is defined by the last 4 data on the nonlinear characteristic. You know that this is the lower part of the hysteretic curve. So starting from quadrant 3 up to quadrant 1, plus 4 more data, and that final 4 more data defines the slope, defines the air core inductance.
Okay, so there are some other questions that have been already kindly answered by Delcio, who knows quite a lot on this topic. So I really, there seems that there is no other open question not answered. Of course, there was let's say a question about showing how to monitor the run in DOS command window, something that you promised that you will do it.
Yeah, okay.
So let's close perhaps the session with this one.
Yes. You see my Windows system with many different ATP draw versions, but now we have used the latest one. And for me, the EMTP command or the EMTP is always executed by this batch file. I think many of you are familiar with. If you open this batch file, it's, I don't know how to increase the format, word, font. I can try to increase a bit. Yes. Okay, maybe you can see it's more clear.
Yeah, it's okay.
The key is this one. You know that EMTP is executed by this command actually. Letter M could be G or even W, depending on which version of which compilation of the executable code you are using. But if you put a pause here, as soon as this command is executed, you have a chance to see what is going or what was going on the DOS window, because this command works in a DOS window. At the ATP draw side, you can control it easily. There is a relatively new, just 3 years old. So, you know, in ATP world, 3 years is nothing. So it's a 3 years old tool. You can make a connection. When you click on execute or F2 quick button, the program actually executes what is written here in the solver field. For me, this batch file is entered here. You can enter directly the TP big exe, but in that case, you will have no DOS window open, and you will have no chance to stop at the end of the simulation to watch what was going on the screen. I know it's an old-fashioned style or old-fashioned way of running EMTP, and I also know it has some drawbacks if you use, if you work with parallel processing and so on. It's not recommended even by Professor Hans Hoydalen. But for simplicity, for simple simulation, for individual simulations, I still use this option, because in combination with that pause, I always see whether any error appeared on the screen, whether the model is created or not.
Okay, so it's already half an hour more than scheduled, the originally scheduled duration of this webinar, but I think it was very interesting. There are no other open questions. I would like to thank, first of all, Laszlo for being with us and sharing his experience on transformer modeling. We will have the chance to be together once again in almost 20 days, in the 16th of December. I would like to thank the European EMTP Users Group for their good idea to start this series of webinars, and of course all the attendees that they participated. There were almost 100 of them at some time, so I think it was quite successful. As I said, this is recorded, and together with some documents and the examples that Laszlo used, this whole material will be one way or another available soon by the EEUG website. So, thank you very much for participating. Don't forget to fill in the survey that you will, it will automatically pop up when you log out, and submit it, and see you in one of our next webinars. Thank you very much, everyone.
Thank you. Bye-bye. See you.